Hello and welcome back to another LeetCode problem. This is LeetCode 1004, max consecutive ones, version 3 of that problem, or the third iteration on it. It's a medium problem. I have solved it before, but that's quite some time ago, so I'm going to give it another try without looking at any of the answers. So let's see what we got. So we're given a binary array nums and an integer k, and we should return the maximum number of consecutive ones in the array if you can flip at most k zeros to ones. Okay. That sounds like a sliding window problem to me. And let's look at the constraints. So we have a limit on the number of elements in nums. For runtime analysis and space complexity analysis, we're going to ignore that fact. Otherwise, everything is O of 1. And time and space. And okay, and the nums array contains only zeros and ones, and actually the array might be empty. Okay, interesting. So it might contain 0. But what is also true is that k is also smaller or equal than the length of the array. Okay. That informs us what edge case we have to take care of. So it's always useful to read the constraints. So let's look at an example. Example number 1. So we have an array here. And we have k2. So that means we can have at most 2 zeros in our sliding window if we use a sliding window approach. So if we use this, we could flip this 0 and this 0 to 1. And that would give us a length of, of consecutive ones of 5. Now if we slide our window one further, we have one too many zeros to flip. So here, the maximum length of consecutive ones is 4. Now, if we go one further, we could flip these two, and then these two, and then we have maximum length of consecutive ones of 3. We move one further. Well, I'm doing a bad example for the sliding window. So this would be the first sliding window. Then we would increment the window until we have more zeros in it than k. And then we would start to contract the sliding window until we have k or less zeros in it. So this would be the next sliding window that we look at. And that length would be 2. Then we could add all of these ones without running into a problem with k. This again now gives us 6. So 6 consecutive ones would be our maximum. And if we include the next one, we have to contract our window again so that we only have 2 zeros in it. And that's also length of 6. So yeah, so I think a sliding window approach where we just count the number of zeros in it works. And we will contract the window when we have more than k zeros in it. And all we need to do is remember the maximum size of the window. And yeah. Here's another example. I don't really think that we need it. We already have a very solid understanding of how we can solve this. And so in terms of runtime complexity, obviously we need to run over all of the elements in the array. So I'm just going to say this is going to be O of n time. And what space? Well, that depends on how we implement the sliding window. And with sliding window, it's kind of good to know that you can implement it like as a deck, like a FIFO, where you put actually elements inside of it if you want to do that. So that would be O of, let's see, what do we have here? O of n space as well. And maybe that's the first one that we'll implement, but you can always replace like the data structure in a sliding window, or almost always you can replace it just by using indices. Using indices is a little bit more prone to making errors with the indices, so I would maybe recommend not to implement that right away. Instead, start with the solution that's probably the easiest. So we're going to start with one where we actually have a data structure that contains the elements that are currently in the sliding window. And for that, we're going to use the deck, which is the FIFO implementation, or an implementation of a FIFO in Python. Import deck. And I don't think you have to import this in LeetCode. I think it's available right away, but in your environment, you might need it. So we're going to have the window, which will be a deck. We will have a result. And in the beginning, the result is going to be 0. And at the end, we're going to return the result. So now what we do is we just iterate over nums. 4, and in nums if, and we will simply add this value to our window, right? Window append n. But we also need to keep track how many zeros do we have in our window, right? So how should we call this? Window zeros equals 0. Why not? Let's call it that. Equals zeros, and then we just do if n is 0, then what we'll do is we'll increase our zeros counter by 1. Now we have to check if window zeros is larger than k. Well, actually we could do a little while loop. This is now the contraction. So if we have more than k zeros in our window, well, we need to remove the elements from the tail of our little window that we're using to slide over the entire array. So and Python has, for the deck, has the pop left method. It's an O of 1 operation. If you use an array, it's an O of n operation. So that's why you want to use a deck and not a regular array. So we pop that value out, and then we do if n equals 0, then we are actually going to decrement our 0 counter, right? So let's do that here, -1. Yeah, so there we go. And now, after these two steps, we can be sure that our window contains at most k zeros, and we can actually say that, well, result is the maximum of our previous result and the size of our window. And that should be everything. And when we run this, I hope we don't run into any issues. Collections. Okay, typo. Collections. And so that works, and we could submit this now, and it should work just fine. There you go. And yeah, and so now let's try the other approach where we reduce the space complexity to constant space. We want, so instead of using a window, we're only going to count the zeros. And but we need to know where we are currently. So we have to have, well, we need to know where the window starts. So we're going to use a left pointer for that. And maybe to save a little bit of typing, we're going to use left. We're going to use zeros to count the zeros. And so that simplifies our code a little bit. And all we need to do is we now need a right pointer that points at the right side of our window in range length nums. But it means the right side of our little window is always where we currently are. So at each step, we're going to increment the window, and then we're going to contract the window by incrementing the left pointer whenever it's necessary. So if we, well, n is going to be our nums right. So if that value is 0, then we need to increase the number of zeros that we have. And maybe we don't want to use the variable n explicitly for that. So that's what we do. And now what we do is we still have to contract our window. So we're going to check if we have more zeros than k. So if that is the case, we can't pop it really from our thing. But what we'll do is we will say if nums at position left is 0, we need to decrease that count, and we need to increase the left pointer. So that's essentially how we do it. Now, to determine, now we don't have the window data structure anymore, but we still need to be able to determine how wide is that window. And we know that right is always larger than left. So first thing we would do is we would calculate right minus left. But what is right and left point at the same index? Well, then this difference is 0. So we have an off by 1 error, and we have to fix it by adding 1 to that. And let me just check if, does it look right? Yeah, it looks kind of right. Let's run it through the test. Check that I didn't make any typing errors, and I probably did. Window zeros, there's no associated value with it. Oh, because I changed it to zeros. That's why. Okay, cool. Now let's try again. So you can see if you rush through it, you make those stupid mistakes. But both test cases seem to pass. And now we're just going to make the submission. And voila, we've reached the optimal solution. So linear time and constant space. Yeah, I would recommend you go and implement this yourself. Try to see, just try to see if you can implement it while talking. That's always a good interview practice. And also try explaining the trade-offs between the constant space and the linear space complexity. Linear space is maybe less error prone to implement. Constant space is of course more efficient. So there you go. I hope you enjoyed this one.